Tonight, special guest from the Johns Hopkins University Applied Physics Laboratory is Steve Conard. For the past 16 years, he's been the lead engineer on the New Horizons long range reconnaissance imager.
Oh.
So, seeing far away with a thing that's far away.
Just an 8-inch telescope, guys.
So, here's Steve.
All right, Steve, welcome.
I don't have much sleep. I'm trying to bring it here.
Well, thanks for having me. The reason why I'm here, by the way, and came all the way up from Baltimore this morning, is to give Dan a T-shirt.
Yeah. It's got to end up that way.
But I've had a great career. I've spent 37 years mainly working building space hardware, a little bit for the military as well. And everybody in this room has paid my salary for 37 years to have a great job. And this is my give back. So I've been going to clubs all over the East Coast. I was just down in North Carolina and Tennessee a couple weeks ago talking down there. And also, I'm an amateur astronomer. That's how I got into my job, right? Finding Saturn when I was 12 years old and grinding my own telescope mirrors in the basement turned me into an optical engineer. And that's how I ended up doing what I do. So anyway, this is my give back. I'm a member of a couple of astronomy clubs too. I know how hard it is to get speakers at times, so I'm happy to do it for people. Okay, so we're going to talk mainly about the Ultima Thule encounter this past January. For those of you who probably heard Alan talk about this a couple of weeks ago, you're going to be disappointed I am not Alan. Okay, so we'll talk about the mission for a minute. Since I haven't talked to this club before, I have a separate LORRI presentation I do about building spaceflight hardware. So I'm going to give you the compacted version of that really quick. We'll talk about what we did to learn about our target. Dan asked me to spend an extra minute or two talking about the occultations we did a year and 2 years ago as part of that. Talk about how we got to Ultima, preparing for the encounter itself, talk about some images and some of the latest scientific interpretations. I am not a scientist, I'm an engineer, but I am staying at a Holiday Inn tonight. It's the first time I've been able to say that. So mission background, so as Alan has been advocating for going to Pluto since I think the late 80s, very long time now. In 2002, they finally got the go-ahead for the first of the New Frontiers missions to go do a Jupiter flyby, go to Pluto, and then go to 1 or 2 Kuiper Belt objects. And just going back to that time, when we launched, or until right before we launched, Pluto was only known to have one satellite, Charon. And there were no known KBOs the mission could get to. We launched within the original window. In January, gave us the Jupiter flyby, which gave us the gravitational assist, which shaved like 3.5 years off of getting to Pluto. The Jupiter flyby was also a really important opportunity for us to shake down our instruments. That's the only flyby we did before we got to Pluto, and that was 13 months after we launched. So we had to get to know how to use everything really quickly. And first reason for going by Jupiter, of course, was to get that gravitational assist. Second reason was to shake down the instruments. The third reason was to get some good science, and we did get good science there. And of course, we flew by Pluto Charon in July of 2015. Highly successful. It'll be, you'll be seeing images my camera took, probably for a very long time because we're unlikely, I think, to send another one back there in the near future. Certainly, that was the high point of my career. The level of recognition and all for that was really neat. And I actually got my 5 minutes on the Discovery Channel where they interviewed me in my home observatory, which was pretty cool. Oops, wrong way, Steve. Okay, the science instruments on New Horizons. I'm just going to go through these really quickly. ALICE is a UV spectrometer. I spent the first 20 years of my career building nothing but UV spectrometers. We then have a color imager and an IR spectrometer in the Ralph instrument. We used our radio dish to actually measure the temperature of the surface of Pluto and also to measure some atmospheric properties. There's a student dust counter University of Colorado students built that bases the direction spacecraft is generally moving and counts the number of particles as we move through the solar system. There's 2 particle instruments, a solar wind experiment and a high energy particle experiment. Pepsi is the other instrument that APL, my institution, made. We also made the spacecraft. And then there's the LORRI instrument down here on the lower left, which I'll talk about now. There's a picture of New Horizons down at the Cape. And I was talking about this, I think, to some folks at dinner about how funny it looked like to see New Horizons, this thing that, the size of a big grand piano, which is a pretty small spacecraft, in this huge fairing for the Atlas V. And the fairing for the Atlas V is big enough that you could put a school bus in. And you just had this little tiny spacecraft in this huge fairing. It just looked utterly ridiculous. But the whole idea, of course, behind New Horizons was you make the smallest, lightest weight spacecraft as you possibly can. You buy the biggest rocket you can and you throw it at Pluto as hard as you can. Here's where the instruments reside. All of them, with the exception of LORRI, are external. And that turned out to be really critical to some of the choices we had to make to build LORRI, because we're putting our telescope in a very challenging thermal environment. You run your spacecraft typically at room temperature, so that way you don't stress your electronics. So imagine we've got a 8-inch Ritchie-Chrétien telescope that's inside a room temperature box looking out at either deep space, which is 3 kelvins, or Pluto, which is 40 kelvins. At the back of it, I've got a CCD. I'm trying to keep it minus 80C. I'm going to switch units on you. In the middle is all 25C, plus 25C. That is not a good situation for your telescope. Here's the New Horizons getting put together, and you can see LORRI right here inside the box of the spacecraft before that panel on the side got put on there. Here's where we're putting the antenna on. This is what LORRI looks like. The secret sauce to LORRI, the fact that we can get it to work well in this challenging thermal environment, is using silicon carbide. So we use silicon carbide for the mirrors and the metering structure. So it's athermal. You make everything out of the same material. If you do a bulk temperature change, you change your focal length a little bit, but your focus location doesn't change in theory. So silicon carbide has 2 really nice properties. It is very thermally conductive, and it has a low CTE, a low coefficient of thermal expansion. Not many materials have both. You can think of your glasses like Zero Door, where they have almost no CTE. They don't change their size when you change the temperature, but they don't move heat very fast. So they can get big temperature differences across them. On the other hand, you can think of making a whole telescope out of pure aluminum. Moves heat really good, but it has a huge CTE. It gets bigger and smaller in temperature. So silicon carbide's big claim to fame is it's good, not perfect, but good in both. Here's a picture of the LORRI silicon carbide. So you can see the whole metering structure here. All this gray material is cast silicon carbide. And this was done by a company that was SSG and is now L3 Harris up in Wilmington, Massachusetts. And they're actually building another one of these almost identical right now for the Lucy mission that we're working with them on. The mirrors are also silicon carbide with an aluminum overcoating on them. In this case, we have a dummy aluminum mirror at the secondary for the testing we were doing at the time. Looking down the baffle tube was made out of composite. So you had your hockey sticks earlier, same stuff. Except below out, yeah, same variety. You see the veins we have going down here. Here's the primary mirror, 8.2-inch primary. Our final focal ratio is about f13, kind of slow. Secondary mirror up here. On the back of the secondary mirror, there's an alignment flat that we use for aligning to the spacecraft. 3-vein spider holding the secondary in place. We have a field flattener, typical Ritchie. You have a curved focal plane. So we have a 3-element field flattener made of fused silica, 3 elements. The CCD mounts behind this. It has 3 flexure mounts that it's attached to. Here's the CCD here. This is an E2V 47-20. And you can get that same sensor in amateur cameras. For example, Apogee makes one that has, I think they use a 4710, which just means they don't have a storage area on it. But the CCD is about 13 millimeters square. It's a 1024, 1024 with the 13 micron pixels. We have a couple of calibration lamps to light up the focal plane. There's a flex circuit here to the circuitry that drives the CCD there. And that's so we can keep the CCD at minus 80 or so C, and then have the board close to room temperature, because the board is actually mounted to the spacecraft. So there's a there's a 100 degree or so C temperature differential across that flex circuit. Here's the CCD mounted to the back. So the FPU box, the electronics box you just saw a minute ago there, is flipped upside down. Here's your flex circuit running down here. There's a mounting plane here that the CCD is actually hanging underneath. And we cool the CCD passively, right? So we're inside the spacecraft at 25 C. We need to get that heat out. So what we have is there's a beryllium bar here that goes outside the spacecraft to a large beryllium radiator. Large, I mean, it's about 9 inches by 18 inches or so. And the way you flexure that, in effect, is use one of these flex weights, which are, I think, 500 sheets of 1 mil aluminum. That's very flexible. It kind of reminds me of having a slinky in your hand. And that way you don't put loads from your spacecraft into your telescope. So you're decoupling of that. Here's LORRI in the clean room, less blanketing, so this is all complete. There's the conduction bar going up to the radiator here. We have non-conductive pieces going down to hold it to where the spacecraft, where we're about to the spacecraft here. We're trying to keep it all cold inside this 25-degree spacecraft. Typically, when you put blankets on a spacecraft, you're trying to keep things warm. We're doing the opposite. We're putting blankets around our telescope to try to keep it cold. Here's the brains of the operation. So 3 4x4 circuit cards. We have a low voltage power supply. There's an imaging interface to the CCD, and then there's a processor. So that whole box is something like that. And then here's it with the blankets on. You can see the radiator hanging off the side here. This is on a vibration test fixture to get ready to go to vibe. All right, so that was my 7-minute version of LORRI that you guys had to get because you didn't put up with hearing me before talking about LORRI. Is there any instrument-related questions before we go on? Sir?
So, with the silicon carbide mirrors, how exactly do you grind and polish them? Because silicon carbide is an extremely hard material. It's literally used as an abrasive to grind normal mirrors.
Yeah, and Tinsley's been doing that for years. So they send the mirrors out to Tinsley, same people who made a lot of the HST corrective optics, for example.
They do like diamond grinding wheel or something?
No, there's traditional polishing techniques. It's all computer controlled.
It take forever to polish and grind.
No, actually, the ones they just did for Lucy LORRI, they did in 3 weeks.
Wow.
All of the electronics seem to have very low wattages.
Oh yeah, yeah. That's the other.
Selected components selected for.
Yeah, the LORRI when imaging, I think I'm drawing a little under 4.5 watts, and that's the other key is we have one RTG that's generating power out of plutonium, 200 watts. I think the ones on Voyager, I think they had 3 much larger ones, if I remember right. But we had 1. So we had to really limit our power. So all of the instruments draw, I think I've ordered 20 watts total, something like that, maybe 25 watts. And we're saving our power to keep everything warm and to broadcast back to the Earth. So our transmitter back to the Earth is of order 20 watts, something like that.
Still, it's just not even a light bulb.
Oh yeah, yeah.
Shot glasses.
Is that why like the CCD isn't necessarily like bad in data transmission, but is in addition to the data transmission rate limit, is that part of why the CCD isn't super high resolution or small pixels? Just because of the amount of computing power needed would suck up more wattage?
Well, a big part of it was 2003 we picked it. And it was picked then as a heritage part because we had tried to fly the same ones on the Contour mission. The Contour mission that failed back in 2000. So the big thing with space hardware is heritage is key. That's why for Lucy right now we're building almost an identical LORRI because we can do that a lot cheaper and we're using the same parts and we can say, this passed, this worked at Pluto, we can make it out to Jupiter fine.
You said there's 3 corrector lenses in there? Or
Yeah, 3 field flatters.
Isn't this like your
Purely
regular?
field
flatters, and they're all in series? Is it?
They're all in series, they're very close to the focal plane, so they're really just acting as flatters.
So it's really just your average RC with a flattener, just made out of more exotic materials than most amateurs would ever touch.
Absolutely.
Is there any redundance or
No.
backup? No.
The only redundancies I have are, for example, the calibration lamps, which I don't need either of. But it's all, LORRI is all single string. LORRI was not required for the highest rated science. So in theory, they could have lost LORRI or kicked LORRI off before we flew for money reasons or weight or whatever. And they could have done the science, the basic science they needed to do without us. In the end, it turned out that, if you talk to Alan will tell you that he wishes, every mission would have another LORRI. Anything else before we go on and talk about the encounter? We've got a lot more slides to go through. I got to get moving. Okay, so as I said earlier, when we launched, there was an idea that, hey, there's going to be so many KBOs they find that once we get to Pluto, we're going to know 12 of them we can go to, not a problem, blah, blah, blah. So in 2011, they started really looking much harder. And you have to realize how hard of a problem this is. With the amount of fuel we had, we could change our trajectory after we went by Pluto by 1 degree. So think of a 1 degree cone. Isn't the tip of your finger like 2 degrees handheld or something like that? So imagine half of that is where you need to go. Not only that, but the KBO you find has to be there when you're there, right? So if it happens to go through that cone 6 months beforehand, that doesn't help you at all. So you're really limiting yourself. And then to make things worse, where of course are we going? We're going right into Sagittarius, the densest part of the Milky Way, and you take some of these deep images that we take, you just see stars everywhere. And you're looking for the faintest thing you can see against that background. So they used, for a couple of years, they used some of the biggest telescopes on Earth, the telescopes, etc. And there was no success. They found plenty of KBOs, they just never found one in the right place at the right time. 2014, they made a request for time on Hubble to try to find a target. And HST has a fainter limiting magnitude than any ground-based telescope. So HST can get to 27.5, ground-based telescopes are limited to around 26. And it has higher spatial resolution. It has a really narrow field of view for what we're doing as well. So they got orbits from the director's discretionary orbits that Hubble has. And I think they had an order of 100 or something like that, but don't quote me on the number, which didn't make the astrophysics community very happy. But they actually ended up finding 3. So here's the finding images, the 5 images where they found what became Ultima Thule, nicknamed Ultima Thule. Right? So there's the 5 points across, same background stars here and here. The other 2 they found, one of them was somewhat brighter, but right on the edge of what we could get to. Another was sort of in between in both the brightness and the direction we have to go to. And Ultima used the least fuel and was the faintest. So once they found it with HST, they kept observing it, kept going back to it, trying to get a good orbit on it, trying to get a light curve. They knew it was a small Kuiper Belt object from how many photons they were getting with New Horizon, with Hubble. They measured the orbital period just under 300 years. They knew it was a cold classical type. That means that it is very close to the plane of the ecliptic, very circular orbit, so it's probably undisturbed, which is what they wanted. And it just turned out, when they started calculating things, that the encounter was going to be on January 1st of this past year. Now remember, when they were doing all those things, they'd only observed up till then about 1% of its orbit, right? There's 3 years or so of orbit. And what could you tell with HST? It's completely unresolved. It's way, way, way under a pixel. So you see nothing resolution-wise. They knew it was about mag 27, so you'd never see it from the ground directly. There might be a caveat there. And they really didn't have enough visits to get a very distinct light curve, but they weren't seeing a good light curve from it. And they knew KBOs could have high or low albedo, which is surface reflectivity. And using the HST data, the estimates they had were anywhere from 10 kilometers across if it was bright white, to 40 kilometers across if it was charcoal black. And remember, we've seen both of those on Pluto. Right, the brightest areas are ordered 50% reflective, the darkest areas are about 5% reflective. So they were all within the realm of possibility. So think about it now, you're doing a flyby, and you're going to go and take pictures with a fairly small field of view, like my telescope is, and you don't know how big the object is. So that ain't a good situation. You don't know how to plan your observations. Remember, we don't do any of this real time. We make our command loads years in advance, practice them, refine them and all, and upload them, and then they just go. There's nothing real time you can do. It's just where MU69 is versus Pluto. We went by Pluto there. We went by Jupiter way in here, and MU's there. So the really big issue, though, was seeing your target for less than 4 years, you end up with a really large error bar in distance from the sun. So now, two things I got. I don't know how big this thing is, and I don't know how far it is from the sun. So imagine that my error bars, as I'm going in, I'm taking images with LORRI, and I'm pinning it against the background of stars when I'm coming at it. So I know in those 2 dimensions very well where it is. But the 3rd dimension, this way, I have a huge error bar. So if you think of the error ellipse, it's like an error hot dog, right? I have a big error in that direction, and I have hardly any error in the others. So now if I turn it around, I say the error ellipse is along the front row here. So imagine I'm coming in to do my flyby, and any one of you guys could be a UT. But I don't know where. I don't know which of you guys is. So here I am wanting to take my pictures. When do I take my pictures? So what you can do to get around it, and we hedged our bets, of course, is we just assume it could be anywhere from here to here. We take pictures all the way down the line, and we got a lot of beautiful background star fields. And we actually get what we want. But still, it would be really nice if we could shrink it down and say, oh, it's between these 2. We'll come back to that in a minute. So after we went by Pluto, and then in fall of, we went by Pluto in July of 2015. So in fall, we did our first of 4 maneuvers to deflect head to UT. You always want to do those as early as possible, because the earlier you do them, you minimize the angle. So you minimize the delta V, the delta velocity, the amount of fuel you have to use to get there. The thruster burn we did to add the 4 of them up was all of 57 meters per second, so 2/3 of a football field a second in time. we're already going 58,000 kilometers an hour, so we only changed the trajectory angle by 0.2 of a degree. We did a few more course corrections later that year and the years after. Generally, we always were doing less than we thought we'd have to do. We were nailing things very well. And then at the very end, right before we got to Ultima, rather than doing a thruster correction, we just changed our delta time. So we had all the command load loaded up, and then at the last second we said, oh, it wasn't him, it's him. So we're going to do everything 3 seconds later, something like that. So in order to try to narrow down how far Ultima was from the sun and get an idea how big it was, in 2017 and 2018, there were a series of occultation expeditions that the SWRI people, Southwest Research Institute, who Alan Stern works for, had to go and see if Ultima would occult a star in Sagittarius, several different stars in Sagittarius. The first was in Argentina and South Africa in June of 2017. The second was in Argentina in July of 17. And then we had another one in Senegal, Africa in June of 18, I guess. And interestingly, since I, like Bob and Kevin, for your club, I do occultations with IOTA, and I've done it for years. I got called into a meeting in January of 17 with the SWRI folks. I thought they wanted to talk about LORRI imaging or something like that. And they said, oh no, we want you to help recruit some amateurs to go to Argentina to do these occultations for us. And they need to bring their own telescopes and they need to pay their own way. So, that was the initial going in position. In the end, what happened was the SWRI folks bought 25 Skywatcher 16-inch go-to telescopes and 25 of the QHY 174 GPS cameras, focal reducers, computers to run them, battery packs, and sent half of them initially to Africa, the other half to Argentina. And then for the second occultation that year, they sent the other 12 or whatever back from Africa to Argentina. The first one, well actually let me talk about Gaia for a second. This stuff was all made doable by the ESA Gaia mission, which is a astrometric mission, which just, I still, every time I look at this, I think this cannot possibly be right, where they are mapping stars to 10 micro arc seconds. Those numbers combined with Hubble going back to Ultima, so we know where the stars are super duper well, and Hubble looking at UT versus the background stars from Gaia, that's how they were able to predict an object that was on order 20 kilometers, how they could predict when it was really a occult star. Our second attempt at Argentina, our first attempt we had a miss. They got some more astrometry from Hubble, found out that it went south of the picket fence we had. We went back to Argentina a month later, very, very southern Argentina, in the middle of their winter, at latitude, I think, minus 46, which is like north of Montreal in the equivalent in the middle of winter, to the city called the City of Winds. And I was the southernmost point on the beach down there. I didn't get a hit, but I was part of the team. We've got 5 positive chords. So these occultations told us there's no ring system that we could detect, so we didn't have to worry about hazards or flyby. Got a good feel for the size and shape of the object, which I'll show you in a second. And we got a really, really accurate target location. And then when they went back and looked at data from, there was actually a middle occultation that Sophia did over the Pacific between the other two, which I think they got a little bit of a positive on that. And then the Senegal one the year after. They got multiple points with super high astrometry on it. So they were able to really narrow that error bar of the orbit down quite a bit. So it came in, it was very important to us multiple ways.
If you remember too, there was that Nova special that they did on you as well. So I don't know if you guys saw that, but there was a whole episode on your team, your teams.
Yeah, and I didn't even get to speak in that one, so it's not worth seeing that one.
Right.
Go look at the Pluto one where you get to hear me.
Yeah, that's true.
Anyway, so here's the 5 chords we got across, and this, of course, was very intriguing. The thoughts at the time were, A, it's a double, and they just happen to be passing in front of each other. B, it's just a weird potato-shaped thing, which there are other objects about this size that have shapes like that. Or C, it's contact binary, which they also saw some examples of. Starting in August of last year, geez, just about exactly a year ago now, we started taking imaging with LORRI. We were in a 4x4 mode, we were in high sensitivity, we're 30-second exposures. I think we took 20 exposures to get our first detection of it. And those images on your right are what we had. So the left one here, this is the star field coat. So they've taken all 20 of them, aligned them, registered them, put them together. And you can see how dense that star field is. But we had already taken the same fields with LORRI beforehand. So then we took those and we subtracted them back off. And that's the picture you got here with Ultima right there. Now, I'll point out, you can see that I tick marks here, and there's a star right there, but that is not Ultima. Ultima is just a blob on the side of that star. But you can see once we did the subtraction, how well that came out. All right, so when you're getting ready for an encounter, what you have to do. So once they decided what target it was, they came up with their science requirements for the encounter. So that means, what questions did they want to answer? So that's something the scientists do. They do consult with the engineers like me somewhat on that. But their initial requirements they come up with, and then they go and they say, oh, that means that to get this, within 10 minutes of closest approach, we have to have LORRI take 137 images. We need to have Ralph do a scan for color imaging, da-da-da. So they flow it down to the different instruments, what they need to do. They divide the timeline up. So if you remember the Pluto flyby, the heart of the Pluto flyby, where we were getting our best data, was probably a order 6 hours, something like that. Here, it's much shorter, much smaller, we're going by closer, so our time where we have the highest resolution is much less. So all the time is really precious. They divide it up, they decide, okay, this instrument gets this 10 minutes that we slew, this one gets 3 minutes, etc. And then your science plan also has to be balanced against your allocations you have to your remaining fuel, how much power you have. Our RTG is getting older, so by the time we got to Ultima, I think we were down to about 180 watts. We started with about 200. So that means you couldn't have all the instruments on you had before, for example. So now you had to say, oh, you get to stay on here and then turn off, and then this one goes on and that one goes off, etc. There's the solid state recorder volume, how much memory you have. Then you have to get all this data to the ground. So deep space network time is precious. You know, we send down of order 2,000 bits a second. So it's, as I was saying at dinner, it's like hearing your old modem on CompuServe cranked up, something like that. And then there's also just basically budget, right? So your mission has a money budget. You can't throw infinite amounts of people at planning stuff. So you're limited by that as well. Then they build timelines for the encounter, which are the real commands you're going to do. This is all done for Ultima a couple of years in advance. So they do timelines for nominal trajectory, where we're going by at about 3,500 kilometers. For the alternate trajectory, where you're going by at 10,000 kilometers in case there was a ring or satellites you had to avoid. And then we also have 2 different systems. LORRI's single string, as we said before, but the rest of the spacecraft is double string. So there's a side A and side B, and the command loads for side A and side B are different and have to be tested as well. So you end up with 4 different command loads in doing this. They all get tested on a software simulator, so a piece of software that imitates the whole spacecraft. So you take the command load, you run it through, and it gives you all the errors that come out. It says, oh, this didn't happen at the right time. Oh, you had a conflict here, you had too much power drawn there. That's what that step's doing. Once you pass that, then we have a flat sat. We have all the electronics laid out on a table in the lab that look just like a New Horizons, except it's flat. And you run it through on that. And that's where I'm actually taking images. So I have a camera in one of my cameras in the lab, looking across the lab, and takes a picture of like a clock on the wall or something like that.
Can I ask one question?
Yeah.
You're doing this when, and where is the satellite while you're doing this?
The satellite is halfway, say halfway between Pluto and Ultima.
Oh, so it's halfway.
And we're doing this in our lab in Maryland.
Okay. Why didn't you do it a year before that? Why did you?
We started doing it right after they picked their target, so it would have been a year after Pluto or something like that. Now, like the Pluto encounter, our first runs of that were like 08. So we launched in 06. We were doing our first runs of encounter in 08, and we didn't have our encounter in 15. So we were practicing for Pluto 7 years.
Jesus.
Yeah. And by the way, before you think about this, this was not my full-time job for those 7 years. It was a small fraction of my job while I was doing other things for NASA and the military.
And as well as most of the team, right?
Yeah. Yeah, the only people who were really full-time on it were the mission controllers and some of the science things. So, that's the good and bad thing about what I do where I worked is you get to work on a whole bunch of things, which is really nice. The bad thing is you work on a whole bunch of things, so you're just scatterbrained, getting pulled in all different directions. But anyway, and as we go through all this, we have our formal reviews we do. So we do preliminary design reviews and critical design reviews multiple times on these loads. Hazard imaging. This was a bigger deal at Pluto. Pluto, they were very concerned about rings and all at that time. But they also had discovered that these smaller objects can also have debris fields, rings, small satellites, etc. So the only way we could try to retire some of that risk was to use LORRI, take long exposures. So as we're coming in the month before, we would just point LORRI at Ultima, and we'd take 100 or 200 images in the 4x4 mode, the most sensitive mode, 30-second exposures, and just co-add them, and then again, subtract off the background stars. So they did 3 sets of those in very end of November, first 2 weeks of December, and then if you put them all together, the image on your right is what you see. The 2 rings are, the inner ring is the desired flyby, the 3,500 kilometer flyby, and the outer ring is the 10,000 kilometer. And there's no hint of a debris field on either of them. Then, I should put something else in here. On New Horizons, it was really neat that the engineers were included in the daily science team meetings. Other missions I've worked over the years, we didn't have that kind of inclusiveness at times. But getting to see them do their job, watching the scientists make the sausage, was pretty cool. And one of the big ones coming into, say, the middle of December to right before Christmas was the light curve mystery. So they've been hammering LORRI at Ultima, taking images almost daily for a month or so, expecting that they get a really strong light curve by then, showing ups and downs and saying, it has a rotational period of 10 hours or whatever. And they would come up with, we think it might be 30 hours, or we think it might be 4 hours. And, they just couldn't resolve it. Kind of surprising. So they only saw these weak variations. They didn't have a good correlation with time. So they started trying to come up with explanations. Now, the first explanation was, well, maybe it has a rotational axis that's pointing at us. Right? So you can imagine a ball with various shades rotating this way at you. You're always going to get about the same amount of light back. Possible. Could it be surrounded by a dust cloud? And that's what's just making it very uniform. And then there was also some idea about a cloud of tumbling moons, which is fascinating. Here's what the light curve looked like. You can see days from encounter. And the different lines are different, 6 different scientists' analysis of the data of the light curve. And there really just isn't anything that grabs your eye and says, oh, it's a 15-hour period. Nice movie they made for a couple of months showing LORRI's view of Ultima coming out of the background stars. Remember I told you earlier, this star is what it's the little lobe coming off of that star. You can see it just emerge from it over there. And again, we background subtract the stars, it pops out very nicely. The encounter period for Ultima began on Christmas Day. We went into encounter mode the following day. This was the first year in my career I actually had to work on Christmas. It was the only holiday I hadn't worked for this year. Didn't get to see my family during that period and all, and my mother made me remember that. But far different from the Pluto encounter, we weren't getting interesting images beforehand. If you remember back to Pluto, a month or 2 months out, we were getting really neat images. So I was getting flagged down, in my vet's office. My veterinarian wants you to explain these pictures to us. It was really cool to be a minor sled. This time we didn't get the minor sled routine at all. But this time, we were sub-pixel till 5 days out. So, in other words, 5 days out, we were 1 pixel across.
Jesus.
So, 1 day out, you're 5 pixels across. That's still not an image that you're going to get your neighbor excited about, right? Our really good images really were just the last couple of hours. We were the primary instrument this whole time because of our sensitivity and our long focal length. At the time, I was, whenever data would come down, it's the middle of the night, I'd have to look at data as soon as it would come down, have to look at the images from an engineering point of view. The nice thing was that we had it arranged so I could look at data from home. So I could just roll out of bed in my bathrobe and see what's coming down. With the limited DSN passes, the 13-hour round-trip light time. Right? We always think of round-trip light time because if you want to send a command up and have it do something, that's 6.5 hours up, something happens, 6.5 hours, get back to know it happened. So from an engineering point of view, troubleshooting, the whole key is how many round-trip light passes it would take you to fix anything. So you were really watching hard, looking for anything, any flickers and voltages, any issues with images, etc. And thankfully we had none at all. LORRI again ran perfectly, and so did the whole spacecraft. So just a map of the flyby. We actually flew over the pole, about 70 kilometers off the pole was the design. Flying over it here, here's Ultima there, there's its orbit. Here's just, probably can't read that at all, but it's the map of the timeline. There's like best black and white, so it's best LORRI imaging. You see how few miles that is, what is that, 5,000 miles or something like that.
15-minute time tips.
Yep. And if you ever see my Pluto talk or one of the other New Horizons people's Pluto talk, I think ours have hour time ticks compared to 15 minutes here. So we went by a little over 14 kilometers per second. We were 43 AU from the sun. Those are our phase angles, and we ended up being 3,540 kilometers away. So experiencing the encounter. As I said, I'm an amateur astronomer. I've been since I was 12 years old or so. There's several other members of New Horizons engineering team who are also amateur astronomers. And being part of this, I think we kind of had a unique viewpoint, getting to see the science being made and also being, part of the instrument team. The sense of discovery, both at Ultima and Pluto, was just amazing. Seeing these images come down that nobody's ever seen before, and being among the very first person on Earth to see them is just, I can't tell you how cool it was. And it was a privilege, like I said, to be part of that science team and hear them arguing about what they were seeing every day. All right, so how do we make the sausage? So one thing we do, and there seems to be a lot of imagers in the room here, so you guys I'm sure do the same, is we co-add images. We effectively, I think, do what they used to call drizzle. I don't know if they still use that term or not. So there's our single image, and then we add them, resample them, and deconvolve them, which is our other secret sauce, is taking the point spread function out as best we can. So we can turn that into an image like on the right there. The rotation movie coming in. And I like what they did with this. This other one came out more recently, where they scaled it and then de-rotated it.
I know, I love this shot.
It's just mesmerizing.
Yeah, it's incredible.
So how do we make high-resolution color? LORRI's just monochrome, so it's panchromatic imaging. We don't discriminate against any photon. We take any one we get. Ralph, on the other hand, does have color, but they're a quarter our focal length. So they have about the same pixel size, so they have about a quarter of resolution. So you take a Ralph color image, and you paint it on top of a high-resolution LORRI image, and you end up with the image on the right there, the combined image. So almost every very high-resolution image you've seen, both of Pluto and of Ultima, are a combined effort from the two instruments. Okay, cross your eyes, folks. It's stereo time. I found the talk so far about 1 in 4 people can do this in a
Can't do
harness.
it. I'm too close to it. If I was back there.
So if we have time afterwards, come up and look on my monitor. You might be able to do it better.
I gotta use so much for that.
There's our combined highest resolution picture. Here's the
Can you give me some idea of the scale of that image? How big are those levels?
let's see, about 20 and about 10 kilometers, something like that. I think I have the numbers later. The other surprise was when they got the first crescent phase imaging back. This is looking back towards the sun and looking at Ultima. And you can't see it in this picture because I didn't stretch it. But what they found to their surprise was, rather than these being roughly circular going off, by looking at the star field behind them, they found out that they're more like that. They're flattened. At first, they thought they were very flat. They thought they were like pancake flat. When they went through and reanalyzed, they ended up with a little bit thicker than that. It's something like that now. It's the best belief of what they got. Yeah, there's your dimensions. So they nicknamed the bigger one Ultima, the smaller one Thule. The bigger one's like 20 by 20 by 10. And the smaller one's like 15 by 15 by 10, something like that. Spin time is about 16 hours since we were actually able to image it. Once you could resolve it, you could measure that very well. One thing we didn't get good data on, and it's just because of the nature of our mission, is the density. So if you don't have the density, you don't get the mass. And since we didn't have anything deflect by gravity or anything like that, the only thing they could say is the neck between the two would break free if it didn't have a density of at least about a third that of water, which really means very little. You get very much expected to be higher than that anyway.
So what's the composition?
We'll get to that. How do we do with our occultation? I love this. This is my favorite. We just nailed it. So, there's your picture overlaid on our circles. And this was really interesting in multiple ways, right? So it's a contact binary. We've seen other contact binaries, like comets, maybe Hydra, Pluto's moon. Now they're so interested in these things, they think they may be 20, 30, 40% of objects out there could be contact binaries. How can we survey this? Well, let's do a whole bunch of occultations. So now I think we're going to see other opportunities in the future to have exotic travel to measure these things because the scientists think it's worthwhile. They may be looking for amateurs to assist. So here's an opportunity. The terminology, I'm going to speed up now a little bit. I love this because this was from one of their meetings. Informal terminology, you got Thule, Ultima, and the neck. There are the mysterious albedo markings, these bright spots. Why is the neck so bright? Some of the dark zones, and there's some lines in Thule that they don't really, well, they don't understand most everything.
This shot always looked like, to me, when you look back at it, it looks like a big snuffleupagus nose on the right side, two eyes, you know, where the bright spots are. So the head's on the left, and there's like this suction tube sort of thing on the right side. I don't know. It looks like a big nose to me. It looks like a face
like
nose.
a chicken drumstick.
So they started informally naming things. They decided that they would, like craters, they were going to name for home states of people involved with the mission. Maryland had the most home state people. I wonder why. So we got the biggest crater. I don't see a Connecticut on here, sorry. There are these bright streaks. There are hills. The hills are the size of real hills on the Earth, you know, hundreds of feet tall. Reflectivity variation, so it goes from about 0.12 to about 0.06, like a factor of 2. So this isn't anywhere near as much as Pluto. Remember, Pluto went from 0.5 to about 0.5. You have the geology, they're starting to work out, you know, what different sections are. There's a comparison, real size, to the Rosetta 67P comet, which also has that contact binary shape to it. Oh yeah. So here's your chemical composition. You're going to be really disappointed. So this is an IR spectrum where the heavy data starts at about 1.2 microns and goes out to about 2.5. One thing that looks like they have a definite detect on is methanol here at 2.3. They don't have a sure detection of water, which is kind of surprising. There are hints, right? So you expect your water bands is marked here and here. So this maybe, yeah, I'm not getting it there. And then what that feature is, they don't know. So the way they have to do a lot of this stuff is they have to make these chemicals in a lab and, you know, cool them down to 30 kelvins or something like that, and then expose them to sunlight at that distance, the equivalent thereof, and take a spectrum. So what I think you'll find is in the future, somebody's going to eventually identify what that chemical line is. So the two lobes are quite different. Ultima looks like it was definitely assembled from subunits, things brought together. Sort of like, I think of like Play-Doh, different colors Play-Doh smashed together. But if that's happened, they don't also understand why it's so smooth. It shouldn't have enough gravity to really pull it down flat like that. And why did some of the boundaries between the different sections sort of just disappear? And Thule looks like it may have been formed differently, and it has some weird boundaries in it as well. And again, why is the bright material in the low areas? What's going on there? Orientation, that makes perfect sense, how it came together. All the principal axes align. Where if you look at another possible contact binary, this again is the 67P or whatever that Rosetta comet is, they don't look like they're aligned, right? The principal axes of these. And then how do you bring them together, right? So you got two objects now that formed that are rotating about each other. How do you get rid of that momentum to bring them together so they form a contact binary? when they have to come together, and I think the latest number is like 3 meters per second or slower.
Just a kiss.
I mean, it's really slow. So, you know, the ideas are, is there something going on with other bodies? Are you throwing other bodies out of the system? Were they formed early when there was still that nebular gas in there that was slowing things down, bringing them together? We also were looking for satellites and rings, so we took, again, a gazillion pictures, background subtracted, and no ring. And I think they're down now to the point of saying that there's no satellites larger than 100 meters across. All right, coming attractions. So we've only got a fraction of the New Horizons data down. I think I'm over half now, maybe 40%. But truth in advertising, the really good images that we knew were really going to be good, we already got, right? You're always going to download those first. But I'm still confident that some new things will come out in the coming months, so I would pay attention. LORRI alone took 3,800 images during that week of encounter. And as they come down, we release them to the public the week they come down. So every Friday we try to do a release, and the release is 8-bit JPEGs initially. So you're welcome to go to this website and download them, look at the precious ones yourself, look for new results that we release on our webpage and other media outlets, and we're continuing to do imaging of distant Kuiper Belt objects. What are we doing there? We have a unique viewpoint out at 43 AU right now, where there's a whole bunch of Kuiper Belt objects that we can't fly by, but we're still pretty darn close to. We have a unique viewpoint in that if you're observing from Earth, you're always observing them with the light from the sun basically in the same direction you are. That's the phase angle. We can look from like 90 degrees or more and see how that light fades off with angle as you go past it. So that's what the curves here are. Where here are Earth observations of whichever one this was. It's on there somewhere. And then LORRI can take data here out at, I guess this is like a 45-degree phase angle and a 90-degree phase angle, and you can see what that shape looks like. And you can compare it to what it should look like theoretically, and that tells you about the surface roughness of the KBO. And the other thing we were able to do is, from those angles, we could also do rotational curves, light curves, like we didn't do a very good job of with Ultima. So we're doing that routinely. We'll be doing another set in the beginning of September, when we do our calibration, our post-Ultima calibration. And that's the credits, and we made it.
How much energy do you have? How long you think it'll keep going?
The electrical power?
Yeah.
The electrical power will continue to decay, but we should be able to at least do some science operations out to 2032, 34,
Okay.
something like that. Well, I'll be long retired.
You showed that LORRI itself took like 3,800 images or something like that. Given the distance and the power limitations, how long does it take to download one?
It's like the full resolution one, I think they're about 25 minutes, a half hour, or something like that. And that's with a 70-meter dish on the ground. So, you know, 20 watts at 4 billion miles.
That's incredible.
Now, Maryland is an impact basin, correct?
Yeah, I think I've heard that.
Okay. It looks like one.
Oh, hold on. I thought you were talking about on Earth. I was wondering where you were. Yeah, they think that probably is, but they're not 100% sure.
Because where I'm going with this is that if it is the amount of energy of the impact can be estimated. Does that give a constraint as to when the impact happened? How
They think that happened before they joined.
that's what I'm saying.
Yeah, it would have busted apart.
It's at the net.
You know, probably a basketball thrown by somebody with some arm strength other than me, you know, might be able to knock them apart. But slight exaggeration. Anybody else?
think I read a while ago that the possible explanation for the bright spots on the neck was like that due to the irregular gravity of the thing, and because the masses are distributed, especially in Ultima, because it's made up of different chunks, so it's not really homogeneous composition. That the snow that like methane ice or whatever was kind of falling onto the neck and then kind of getting stuck there.
Yeah, that's one idea. There's multiple different ideas that we're working on right now. Initially, that was advertised quite heavily. But I don't want to say they're backing off. I just think they have other ideas now that may also be valid. Anybody else? Thanks for having me.
Thank you, Steve.